Okay, so we're going to talk about calorimetry, which is basically means measuring heat, calorie being the old term for heat. So specific heat capacity is something that we talk about first year chem. Its symbol is CP. I'm not sure why it has a little p. I think it has something to do with pressure. The units are joules over grams degrees Celsius. The specific heat of water is 4.184 joules over grams degrees Celsius, and that is actually quite high for a substance. Water really does a good job of storing heat, and that heat, that's what this refers to as, is how well it can store the heat inside itself. And it is extremely good at it because it has such a high specific heat. It can store it in rotational, translational, vibrational motion. The equation for calculating heat, this means heat right here equals mass times specific heat times temperature change. And that's the equation. And delta T is specifically calculated as T2 minus T1. It can be in degrees Celsius or kelvins because they end up subtracting the same way. But it's TF minus TI, the final temperature minus the initial temperature. And you might get negative numbers here, okay? It is also possible you could see specific heat in terms of joules over moles degrees Celsius, in which case the M has to be in moles to make it work. You're not going to see that very often. Most often it's this. So, sample problems. Says specific heat of graphite is given. Calculate the energy. That means you want Q is needed to raise the temperature of 75 grams of graphite from 294 Kelvin, or if you want 21 degrees C, to 348, or if you want 75 degrees C. So Q equals the mass, 75 grams, times 0.71 joules over grams degrees C, times the temperature change. If I do 21 from 75, so 75 minus 21 is 54 degrees C. If I do 348 minus 294, it's 54 Kelvin. Either way, doesn't matter which one you use. Multiply it out, you get 2876 joules. It is positive because heat was absorbed by the system, the graphite. Okay, it took in the heat from the surroundings. Okay, next one, a little bit different way of doing it. 753 joules of heat to raise the temperature given. So Q equals MC delta T, 753 equals the mass 135 times 0.90 times, and I'm just going to write it as delta T because I think that's a little bit easier for me to understand algebraically. I don't have to distribute, makes it a little simpler. Delta T is 6.2 degrees C. So it took in heat. What's going to happen to the temperature of the aluminum? Well, temperature is going to have to go up. So if TF is greater than TI, and TI is 65, then TF has to be 71.2 degrees C. Okay? Next one's a little bit harder. And this is something, again, we teach it in first year chem. So you have two things going on. You have a system and a different system. Okay? Or one's surroundings and one's the system. I would consider the water to be the surroundings, and I would consider the copper to be the system. And the final temperature of both water and the copper is 21.8. So you've got all these numbers. It helps sometimes if you can break it apart into a chart and kind of see what's going on. So put all your variables in here. So MC, TI, TF, delta T, and Q. So the mass of the metal is 46. Mass of the water is 75. Specific heat of copper we don't know. Water is 4.184. The initial temperature of the copper is 95.4, and the initial temperature of the water is 19.6. The final temperature of both is 21.8 and 21.8. So if you think about it, it makes sense. You're taking a hot piece of metal, you're putting it in some cold water. The water temperature is going to go up. The temperature of the copper is going to go down a lot. Metals generally have very low specific heats. They don't store very well. So we need to figure out the delta T for both. So if I do TF minus TI, I get 2.2 here. And if I do TF minus TI, I get a negative number. But again, that's because the metal lost heat. It's exothermic. So I can calculate Q for anything where I have all the numbers. So the Q for the water, which is 46.2, sorry, 75, wrong number, 75 times 4.184 times 2.2 is 690 joules. And notice it's positive because it took in heat. This is the surroundings. This is what we measured. Okay? Since we measured the surroundings, the system is going to have the opposite sign. This is endothermic. The system will be exothermic. So I put in negative 690. Again, a convention, but it makes the math work. And if you notice, I have a negative value for my temperature change and a negative value for my heat. So that should always match. Do the algebra, X ends up being 0.203 joules over grams degrees C. Okay, last problem. So, and this is a little bit harder. Again, I have two things. I have a system and I have a surroundings. Okay, I'm going to set up my little chart, metal and water. Two things going on. Mass is 125 for the lead. Specific heat is given. The initial temperature is 95. The water is 75. Specific heat is given, and its initial temperature is 25. And they want to know the final temperature of the mixture. So if this is MC, TI, TF, delta T, and Q. I don't know what the final temperature is, but I know that if they've been sitting together long enough, they've had enough collisions between them, that the temperature final for the metal is going to match the temperature final for the water. So to do delta T, you take TF minus TI, X minus 95, and X minus 25. But we got to solve for X, and we have no situation. I don't have the system or the surroundings where I have a number, but we do know that the heat lost by one system is equal to the heat gained by the other. So when I put this in, I'm going to put in the Q for the surroundings as X minus 25 is the temperature change, times the mass, 75 times 4.184. And when I do the algebra on the system, I'm going to do the same thing. I'm going to say it's X minus 95 times 0.875 times 125. And all I know is that the Q for the surroundings is the opposite sign of the Q for the system, but they're equal to each other. So what I'm going to do is I'm going to set them equal to each other algebraically. X minus 25 for my water times 75 times 4.184 equals negative, and you got to put that in there, X minus 95 times 0.875 times 125. Okay, you have to be careful with your algebra. So if I rearrange it and I distribute, on this side I get 313.8x minus 7845 equals negative 109.4x, because that negative carries through, plus 10390.6. I'm going to combine like terms, do some algebra. I end up with X is 43.1 degrees C. And that makes sense because this temperature here has to be somewhere between 95 and 25. Kind of makes sense.